Yeah, hello everyone. Welcome to the whole new topic, virtualization. I'm Shrikanth. I work at IBM, and I have Ilya with me. And we're going to talk about Paravirt Scheduling, a framework for better CPU usage when you see from system point of view. So this is a continued topic from last year from bus and the last year before that. Okay, so coming to the problem statement, right? So you have virtualization where you have multiple VMs across different guests, and you have host, which is managing all the physical CPUs. Here you have 5 physical CPUs, which are called pCPU, and CPU within a guest is called as vCPU, where you have here 10 vCPU, you have 1 to 2 overcommit. This is a common practice in large systems to have overcommit. It may not be 1:2 ratio, but it is definitely in between 1 to 2. So you can have users come and go, and they can make use of the VMs as they please. And it becomes it's okay scenario because that way you have the best resource of the system. But when multiple VMs do become active at the same time, then you have the contention for the physical CPU. You can see here all the green ones become active, then you have suddenly 10 vCPU threads in host. You have only 5 CPUs. You can only schedule 5 vCPUs, and means one vCPU has to wait for another one. And in this, theoretically, you will have 50% steal time in each of the guests, right? And that's expensive because vCPU preemption could be expensive for a couple of reasons. One is vCPU context. Because the host doesn't know what vCPU is running. It could be holding a spin lock, it could be holding a mutex, it could have disabled hierarchy preemption or something like that. And so total progression of the workload gets delayed. And then there are different hypervisors which have different level of granularity of scheduling, additional overheads, and TLB and cache thrashing on CPU migration. All of that adds into the total cost. So in this case, theoretically, when we have contention, we should see like 50% reduction in throughput. That's expected. But in reality, we see like 70 to 80% reduction in throughput. And that's the gap that we are trying to address here. And one of the constraints here is we support Linux runs on different hypervisors, some proprietary, some KVM, all that. So all of that gets into picture, and we don't have currently any interface from guest to host. That's no way guest is telling the host, okay, this is my context of vCPU, and there's no communication between guests, and that's even a layer violation, so it's not possible at all. So what we are trying to do is, idea-wise, it's quite simple. You just try to do coordinated way without communication between the guests. You try to do back off from using certain vCPUs at runtime. And this is done using the steal time. Steal time is already an infrastructure which exists in most of the architectures which support virtualization. So you get the steal time. Based on the steal time, it's indicating you have 50% steal time. So in this case, you end up using 50% less CPUs in the guest. So when you combine across all the VMs, you can still satisfy the CPU requirement, and hypervisor stays happy and guests become better performance. Like we are instead of 70% drop, we'll be in like 50 to 60% drop at worst case. And this helps the guest because now if a thread in guest would have done preempt disable or it's holding spin lock, it will run to completion because you have multiple threads, but it would have disabled. No other thread can preempt it because that's disabled preemption. So you get the advantage that way.
So the 3 and 2, of course, nicely makes 5. But what if you have a 3 and 3? Then
yes.
that ends up being an infeasible wait scenario. And what will the backoff then do? Will it?
Yeah, it's still better than 6 and 4.
Probably.
Yeah, that's why I said we cannot theoretically achieve 50%, input like reduction, but something like 50 to 60% is what is a feasible option.
So just for me, you're monitoring the still time to decide to reduce it.
Yes, in the guest. In each guest knows the steal time already today, and it's all accounted automatically. There's no additional mechanism is needed. Okay, this one we discussed at LPC in a bit more detail. I'll quickly go through. So what we need is a mechanism to restrict the workload to less certain number of CPUs at runtime. There are different ways to do this. You can say explicit affinity, go and tell the user to pin the workload, but that is not possible. And then you have hot plug and isolated CPU set partitions on the fly. That's expensive. But even then, the bigger concern is it breaks the user affinities. So when a user has specified affinity in the guest, and that CPU goes offline, its affinity mask is reset today. And that's the ABI today, and that's okay because user is driving the hot plug event. He knows what is going on, and it's not driven by kernel. Whereas here it's driven by kernel, and you can't reset the user affinities.
And in this case, when so if you have one affinity on a non-preferred CPU,
it will continue to run there.
Okay.
Yes.
So hot plug is not a sufficient solution for scaling down the guests with a smaller number of cores. But if you had the ability to rerun the guests with a smaller topology per guest, would that solution be strictly better in this?
That's what currently done today when you see steal time.
Okay.
Either you have two options. One, you change the guest to reduce the number of CPUs it's going to run, or you increase the host capacity. But here, host is already at the system maximum level. We are talking about like 2048 CPUs. It's fixed. It cannot increase anymore. That's not a possible option. So yeah. So at LPC 24, we introduced the problem statement and we had a POC at that time, and it was based on load balancer. We had a new type called CPU part, and I know the name's not great, but it was a bit slow because it was based on the load balancing, and it took quite a while to move the task away from certain CPUs. And at last year, we moved to a push task based mechanism, and it's more of policy driven, and it works fairly fast in moving the task away from CPUs even under high contention. Okay, so some of the design goals that we have considered when doing this is keep the total number of runnable CPUs equal to the closer to the pCPUs. You can't guarantee this, but it will be somewhat in the range. And then preserve user affinities and keep the solution scheduler native, so it works for all the architectures by default without any custom patch or custom user space, and supposed to be lightweight so that you don't have much overhead when there is no steal time. And keep the debug tunables, because steal time in one architecture of, let's say, 5% need not mean the same amount of regression in other architectures because micro-architectural reasons. So we need to have some kind of a debug tunables to adjust based on the platform. And then introduce a new CPU state so that this information can be easily consumed by user space or other drivers, so that they can schedule only on these CPUs and make it work for different hypervisors across the industry. So coming to the new CPU state, we are introducing a new CPU state called CPU preferred mask. It represents the CPUs which the scheduler should currently prefer. It's not a hard exclusion, like affinity is still respected. It's dynamic, it can change on the fly. And the key thing is we are trying to maintain this design construct of, today we have this construct already, like online is always a subset of possible CPUs, right? So we are trying to maintain preferred is always a subset of online CPUs. So you don't end up preferred CPU as offline CPU ever. Okay. Did I go fast? Okay. So we are introducing a new SCAD feature called Steel Monitor. It runs in tick and it computes the steal time periodically based on the threshold. It looks at the steal time across all the CPUs using the CPU stat called CPU time steal. And if it's based on a certain threshold.
So doing a for all CPUs in the tick is a really bad idea.
It's not in tick. It kicks off a work function and that work function does this.
Okay, because you said it's tick based.
Sorry.
On.
Yeah, my bad. I missed the in-between part. Yeah, tick, we call this if the feature is enabled and then we check the time. If time is due, we go and kick off a work function. That work function will do the work. Because it need not be that accurate, it need not be very fast. Just because we are looking at timeline of seconds, not schedule microseconds or nanoseconds that way. Yeah, the logic is kind of very simple. One can say one dumb, but it's like just reduce the number of CPUs by one core, like a stepwise approach. If it's greater than certain threshold, now reduce the number of CPUs, like preferred CPUs, reduce it. And if the steal time is below the certain threshold, increase the number of preferred CPUs. That way you avoid and try put some simpler heuristic to avoid oscillation. Like if steal time is consistently high, then only you honor the values.
So it's not hypervisor driven, but this is guest driven.
Guest driven.
So then you rely on guests being nice to one another.
Yes.
Does that work out?
We have to, at some point, guest have to run the same kernel if one is interested in this, achieving in a coordinated way. If one guest doesn't run with this feature, then yes, it can exploit other guests.
To run a non-Linux guest.
Right. Yeah.
Goes out of the window.
One question, so you are monitoring the sum of steal time on your VM.
Yeah.
If your steal time increase, you decrease the number of CPU. Then your steal time will decrease.
Right.
So you will add one more CPU. So will start. I mean, don't you have this kind of ping pong where you're decreasing and then because you don't have any steal time anymore?
Yeah, that's
can increase. In fact,
yeah, that's a possibility. Yes, we can have oscillation, but at some point they should reach an equilibrium. It may not reach immediately, but at some point it should.
You need some steal time.
Right. And you may have to play around with the high threshold and low threshold to reach an equilibrium state. And there's no way to determine that across all hypervisors, all architectures. That's why I kept the debug knob so that one can play around and give the feedback on what should be the default values.
It also means that the threshold that you're using each VM must be aligned so that they will reduce.
Yeah.
Otherwise, you can have one that accepts a higher steal time.
Right.
And the other one will continue to decrease its number of virtual CPU to reach lower steal time.
Yeah. Yeah, one can do more aggressive tuning, like one maybe more depending on the VM. But yeah, start off somewhere, put a conservative value so that they're not too aggressive.
How long does it take from reducing preferred CPUs to not actually affecting something?
Come again?
So if you reduce it in the work function on tick, how much time does that take to actually?
It's close to one. Everything moves off from the, let's say you're gonna have like one task or two, even 10 tasks. It takes approximately very minor second. For example, if you learn MP start, all within a second it moves to a preferred CPU.
One question.
Yes.
So you assume that the guests are kind of floating instances, right? Usually, I mean, majority of the guest instances are paired to physical CPUs. So it can't overflow to other CPUs. That's not
It might. Yeah, vCPU. If you have vCPU pinning.
That's the usual case.
Yeah, but yeah, in our case, we don't do vCPU pinning in our solutions. We have something called SPLPA, that's shared processor helper. It's a VM, nice name for VM, but yeah, we don't do vCPU pinning there.
And if the guest is kind of overflow to other CPU, then you can actually you should expect some performance problems, right?
Yeah, but vCPU, if you have pinned every vCPU, then you cannot do much. If you haven't pinned all the vCPUs, then you can still migrate the task off to vCPUs which have been pinned to the host. Yeah, right.
Yeah. If you completely do a hot unplug event, it's clear that the guest knows that there will be no further instructions executing on that CPU, so it's not going to depend on it anyway. I guess one thing I haven't been super clear on here is what are the criteria that the guest has to meet to prevent starvation? Do the non-preferred CPUs just run infrequently, or do they never run? If there's anything waiting to happen on those non-preferred CPUs, can the system starve?
Yeah, idea is not schedule anything on it for now, unless it becomes preferred. Yeah, we will come to that in the subsequent slide on how we are trying to do that.
Yeah, so the skill monitor, it manages this mask. Does this actually look at what CPUs are active and then reduce a CPU that's been idle for a while? Or
yeah, online CPUs.
But does it just take a CPU from the end? Does it shrink the mask linear fashion, or just
right now it's right now it's simple. Just takes one core at the end of the online mask. That assumes there are some assumptions we still have. It doesn't do NUMA splicing, but yeah, and yes, question.
I maybe misunderstood something. Do I understand correctly that if you have a task that always task sets itself, or root task sets itself to unpreferred mask
right
CPUs, then the whole approach is broken?
Yes, to a certain extent, but let's say in that case, you will still see steal time, right? You will not pin all the workload in all the cases. If that is the case, then none of the solution can help. If you have some workload which is only pinned to non-preferred CPUs, you will still see steal time. And if you see steal time, you will take out another set of CPUs which may be preferred now, but that will not violate the task set heuristic. So that way, you kind of leave the non-preferred CPU running, but you will take out another set of preferred CPUs as non-preferred, and that kind of helps you to achieve the lower steal time.
Going back to the oscillation question.
Yeah.
You say that it stabilizes at some point, right? But what happens again? What happens if the activity in the guest changes?
Yeah.
You will need to go to recalculate the time and have some more time to stabilize.
That's true. It is currently a stepwise approach, so it may not drastically drop, but it will have waves. But yeah, we probably have to take input from maybe PID controller to kind of smoothen the graph, things like that.
So the ACPI systems also have this rack management crap in, where they try and do inter-machine thermal management in a rack system, and then they impose thermal threat. So the rack management will then try and tell a system to use less energy. And I think currently that's implemented with forced idle, but I forget. Yeah. Yeah.
That's global to the machine. That's not per CPU.
Yeah. So
guest knows about this today? Guests know about this?
No. It's the machines, that's the hosts that need to lower their thermal output. And I think we just force idle a random CPU or something, but it has issues.
So how many CPUs?
Oh, it gives you a number?
Yep.
Yeah.
Okay. All the information.
The signal to the machine get an interrupt.
Yeah, it's through the ACPI magic.
So ACPI magic generates an interrupt.
Well, it's
not
really ACPI magic. It's just an interrupt from the PMC.
Okay.
then basically,
Then you find out this is how many cores I'm allowed.
and there's some AML processes that sees that, oh, this is about the thermal, and then it will generate a notify, and then you can handle it.
Right. But that gives you a number that doesn't tell you which ones.
Right.
Yeah.
So
Which is a bit the problem here, because it works the other way around. It finds out which vCPUs are already not making a lot of forward progress and elects them as preferred. That's accurate, right?
So it might make sense to try and unify some of this because it's a similar enough constraint.
So
Yeah.
So in that case, if it's a thermal limitation, will the CPU yield just fail?
I think currently we run a 501 task that is basically a fake idle loop. So if there is real-time workloads, it will not actually go idle. But for all other intents and purposes, it will run the hold instruction. So it's
right, but there is some custom thing that needs to be replaced with that stuff that you are talking about.
yeah.
So that means these CPUs are not available to the host anyway, right? To run this.
But
This is in the host.
If you transpose that to a guest, you could have your guest entering a low power state, which you emulate
maybe
in the architectural way you want in your advisor.
Maybe just pass a signal to the guest and then guest can reduce.
Use this preferred solution for the ACPI thing. It would also go idle for not having any work to do.
Yeah, same thing.
Yeah, so both have the constraint that we need to reduce the number of active CPUs.
Yeah.
And I think it might make sense to look at unifying that a bit. Okay. If we're doing this extra CPU mask anyway.
Okay. So if I understood.
So there is this Intel Power Clamp driver. Also,
we have two forced idle things somewhere, right?
But so the other ones use the same underlying mechanism, but this ACPI thing still has to be worked.
Of course, yeah.
Anyway, so you can basically
and
force idle or others.
Right. So does it have topology awareness? Because at some point, Arjen was babbling about trying to offline an entire package that's more efficient than just random CPUs. But I don't think that ever got anywhere.
This piece doesn't.
No.
Well, also, it's hard to say because the firmware only tells you the number of CPUs.
Yeah, but then you can. So it says 4. You pick 4 in the same.
Yeah, so the interface is just.
Peter, I don't know if you remember something called CPU pulse that we proposed.
No, I have no memory.
You remember? Yeah, so that's kind of similar problem back then. Like a CPU pulse, instant black hole, but temp. From the point of view of scheduling user tasks.
Yeah. So this is a soft
affinity
thing,
kind of.
and it just tries to not run stuff.
CPU pulse was a little bit strict about it. Because even with the idle injection out there, we still have some activity that can run because it can't run anywhere else.
CPU pulse was like.
Yeah, that's the point, and we don't want that in this CPU pulse.
Can you make this as like thermal pressure in some way? So if your CPU pressure, you say tell the guest it's under thermal pressure.
So yeah, there is some external pressure in In this case, it's steel time, the thermal or
Yeah, currently we don't.
power constraints or whatever.
Right. And still time is, we already have it today across all hypervisors. Why do we even need a new interface to do the same thing?
The still time is already accounting in the CPU capacity.
Right.
CPU capacity will decrease.
Right, so this is just a faster way to.
Right.
The main problem is that even if the CPU capacity goes to a level,
It's not going to zero per se. We don't go to zero, and
even if we have a capacity of 1,
right.
we still try to keep one task running on this CPU because it's always like right now in the
Right.
production, it's better to have your own CPU than sharing a CPU. Now you can probably add more.
Yeah, but it's not a policy based. Like it's not.
More
It's more of a number based than policy, right?
capacity of 1. I mean, yes, just to compare.
But then you can still go to capacity 1 if you have higher hierarchy load on the CPU. It need not anything to do with still time.
Yes.
Yeah, these are some of the core APIs that we modified, and one is the CPU allowed. It basically called in the select fallback RQ in the wake up path when you don't have a CPU, and that tries to select a preferred CPU. As Yuri pointed out, Yuri Noro on the mailing list, there are some corner cases which we have to get it fixed, but we tried, if the task is only on a non-preferred CPUs, we let it continue to run there. And we try to avoid overhead for the majority use case. Then the second one is available idle CPU, which is extensively used in the wake up path. This gets rid of some of the hackery that we had in the previous series where we're sprinkling around CPU preferred everywhere. And then CPU priority find, similar observation there. We are sprinkling the CPU preferred check everywhere. This automatically takes care of push CPU mechanism that we have for RT, where we currently push. If we are trying to pick a CPU to push a RT task, and we only do for an online task today. We'll also do it for if it's online and preferred.
And what about the load balancer?
Yeah, I'll continue. Okay. Yeah, so how all of this fits together? If you see from macro picture. So at schematic, we have a push task mechanism. It's going to push the task out if it is on a non-preferred CPU using a stopper. And that way, first you get the tasks out of the run queue on a non-preferred CPU, and on the wake up, you only choose a preferred CPU, so you don't end up on a non-preferred CPU, and you load balance only among the preferred CPUs. So they kind of work with each other and they don't fight with each other, but load balance ends up pushing a task on a non-preferred CPU, so there's less fight with each other. And all of this, the previous cases have been taken care not to break the affinity anywhere. And if task is bound only on a preferred CPU, it will continue to run. This is the patch series, current patch series, which has been posted. Any questions? Yeah. So these are the current state information and the debug tunables available. We have a new CPU state called preferred, which sits in the same place of online possible today. And we have a new scale feature called steel monitor, which user can go enable and disable. And we have debug tunables here, 3 tunables called high steel value, low steel value, and the period. It's currently defaults are very conservative, but one can go and configure the value for an aggressive or more conservative approach. Yeah, now I'll hand off to Ilya to speak about S390 and performance numbers.
Yeah, thank you, Shrikanth. So I work in Linux on S390 team, and I'd like to talk about what challenges we have, how we solve them today, and how Shrikanth's patch we think will help us solve them even better. So I think the main problem that we face on S390 is there is no such thing as bare metal S390 between Linux and hardware, we have at least one level of virtualization. This is our firmware hypervisor called Prism. On top of that, we can also have KVM, for example, and the hardware is optimized to handle this nesting, but that's beside the point. The problem is that this hypervisor is highly unlikely to add Linux-specific enhancements. So there were ideas floating on the mailing list, how the guest can communicate to the host, please don't schedule me out in the next microsecond or something like this. With this hypervisor, this is unlikely to work. And also our users overcommit heavily. So Shrikanth mentioned, like normally it's less than 2. We've seen 3 to 1 at some point. And of course, steal times are quite high and the guests see them. Yeah, and last but not least, we care more about whole system performance because probably, yeah, as was already mentioned, guests can play tricks to get more CPU time from the hypervisor at the expense of other guests. We're not interested in that. We really want to see that the whole system performs well and not just an individual guest. And already today we have 2 features in upstream. One is called HyperDispatch. It was created by my colleagues a few years back. Basically, what happens is that Prism has a feature where it gives priorities to CPUs. So the CPU can be high, medium, or low. And if a CPU is low, then the hypervisor is likely to steal it quite frequently and quite aggressively, meaning for prolonged periods of time. Of course, if that happens and the CPU holds a spin lock, that's a catastrophe, a huge lock contention. But also the problem is that if Prism steals something, the exit from guest to Prism is quite expensive. So we want to reduce both. And in order to reduce the number of exits, we have this HyperDispatch feature where we say if we have a low CPU and we observe steal time on that low CPU, then we lower its capacity. And this works fine until we have really high load, because if load is, let's say, medium, then we just don't put work. The capacity helps us avoid putting work on these CPUs. But if we have 100% load, then capacity doesn't help. Still, the whole guest is loaded. So that's why we're interested in Shrikanth's patch, because it will really allow us to completely avoid putting work on these low CPUs while the system is under heavy load. And another feature is warning track interrupt. This helps us deal with lock holder preemption to some degree. Basically, what happens is that this Prism hypervisor has a feature that it can notify the guest that it's about to steal a CPU. And what we do in this case is we wake up a special real-time thread. So I guess that's what was already mentioned. That's yet another instance of this trick. And what this real-time thread does is just immediately yields to the hypervisor. And the idea is that if the workload that's about to be interrupted is already in critical section, then it doesn't really help. But there is a chance that it may want to enter critical section, and this prevents this from happening. So yeah, that's what we already have upstream, but we think that, again, really preventing putting the load on these CPUs in the first place will solve our problem better. So we have some numbers. So this is what Shrikanth measured on his power machine. So these are 2 benchmarks. One is day trader. This is supposed to be a realistic stock trading benchmark. And what he has is double overcommit, so 2 to 1 on 2 virtual machines. And you can see that, yeah, it's a clear win. And the same is for Hackbench. So for Hackbench, here it goes the other way around. Hackbench prints runtime. So it also goes down in these conditions, under these conditions. We also evaluated that on our firmware hypervisor using simpler benchmarks, so StressNG and uperf. And we have seen tremendous improvements in throughput, even for CPU-bound ones. And yeah, we can see that.
So this is switching from capacity aware to the preferred mask?
Yes,
okay.
Yes. So we really see that under overcommit that helps a lot compared to our existing solution. And we were also wondering if this could help everyone else. So if you just run plain KVM under overcommit, what would happen? So we did this systematic evaluation where we spawned different number of VMs with different amounts of CPUs on each, and then ran 4 benchmarks in each. So as you can see, there are no regressions, or even if there are some, they are lower than noise. They are smaller than noise. For CPU-bound workloads, this doesn't really help too much. But for things like Hackbench, the improvement is very good. So this is S390 KVM, and this is Intel KVM. So basically, same picture on both. Right. So Shrikanth, I think. There you are. So I'm giving it back to you then for the open questions.
Yeah, thanks. Yeah. So does this seems like a probably right thing to do for all the hypervisors, because it's kind of reducing the contention anyway across the system, and it could even work with other designs or solutions that we will have in future, right? For example, let's say there was one patch series from Wengpeng Leon yielding the CPU if it's on lock holder or something of the sort. It could even work well with this, because anyway we are reducing the amount of steal times. The number of lock holder preemption will automatically reduce, and it can work on top of this. It can even work with the R6 solution. We have time slice extension to even get rid of the user space preemption in the para-virtualized cases. User space can do time slice extension to get better lock holder preemption issue in the guest, and then guest can use this to get a better performance in the vCPU preemption in the host. Yeah, I think one major question would be how upstreamable is this? What does people think, Peter?
I've not seen the patches. I mean, I've seen them in my inbox. I've just not.
You saw the subjects.
Yeah.
Yes.
It's on the to-do list.
Okay.
But just not gone around to it.
Yeah. Okay. And is there any non-SMT systems interested in this? The reason I put it here is kind of I didn't want to put too much if referee everywhere.
Isn't the typical guest non-SMT?
Yes, it is. Okay. Oh, all right.
Why do you mention non-SMT? How is it special for?
The reason I'm taking one core out is because PowerVM does kind of a gang scheduling for a core level instead of individual thread level. That kind of gives the best performance.
So that's a power special.
And then even we measure the KVM in the x86, it does still better than doing individual CPU one at a time. Could be like slightly faster to get rid of the CPU, less CPUs. So that's why the default has been put it into one core. That's why I have the SMT mentioned here. We could even do very well for non-SMT systems, but the reason
if we want this to scale to other architectures that are majorly non-SMT, like that would have to work. I mean, that's
you've got SMT.
They have on SMT, right, on the server system?
It has SMT.
Server system has. I saw the patches some time back to enable the control flag.
I have seen one. But I would say for non-SMT system, the CPU is a core, so curious to see exactly what's the difference in your code.
Yeah, I mean this.
Just the SMT mask.
Right.
Just one. It's just the one.
It's one.
Yeah. Maybe that CPU mask of just a CPU will probably work, and that may get help rid of a lot of if. I didn't want to put too much if free there, so that's the reason. Then coming back to that oscillation question that Ricardo has raised, we're looking into PID as a probable choice. The proportional integral kind of smoothen the curve out. That's future work in question. The next one is bit tricky. Like, do we even care about IRQ balance not running? I see it's mostly true in most other distros anyway. Are there cases where IRQ balance is not running? If not, just patching the IRQ balance should help to push the IRQs of the non-preferred CPUs. It's doable because it's anyway it currently looks at the changes in the topology every 10 seconds or so. So that should work fine.
Yeah, so just one word of caution on that. There's a few machines in the wild that simply that are massively SMP, not as a TSMP, where you can't control the affinity of interrupts at all. Okay. So the hardware just round robins randomly.
But then IRQ balance D won't actually do anything.
It won't be able to do anything, but it means that targeting a non-preferred CPU, on these machines that will happen. But yeah,
okay.
As far as I'm concerned, it's shit hardware.
Okay.
Right.
Then should we care about SCADXT?
Probably.
I mean, it's only a matter of just adding one more check in the SCAD that push task, just push the, even if it is SCADXT, I think that should work.
Or you want the callback, right? Because you don't want to be checking.
You are currently doing for offline CPUs, right? For SCADXT, it should work for offline CPU.
You know, it's if there's a way to access the preferred mask,
yeah,
and there is, I guess, it's just a CPU mask. We just use that from the BPF schedulers.
But you don't want to be constantly checking if your preferred CPU mask has changed.
But
you ideally just.
You should be checking for offline CPUs today, right?
Is it done like on task wake up, for example? The scheduler may decide to check the preferred CPU and move to tasks at that point.
Yeah, I'd wake up.
Yeah, select CPU probably and select NQ.
The select CPU callback. If we have access to the preferred CPU mask, we have the option to use that.
Okay, yeah, I'd wake up, but I was thinking if it's like running or something, you don't want to be checking a tick if your preferred CPUs haven't changed. You just want to get a callback and then decide to re-queue or not.
I mean, I would say this is up to the BPF scheduler.
Right, but you need to provide
an API.
Yeah.
Yes. And the API could be give me the preferred mask. No.
Yeah, but I'm saying like I'd want to be notified when it changes because that makes it much lower overhead.
Instead of constantly rereading the preferred mask.
Yeah.
Maybe we can have a user space tool which can monitor similar to IRQ balance does today.
I mean, at the time zero, we have a possibility which is, a key find that, or maybe even from BPF, I can already access the preferred mask. And that already works. And then eventually, if we have a way to get notified when the chip CPU mask changes.
You can stick a K-probe in there.
Yeah. I think we can already do everything in BPF without any additional change to the curve.
It's not pretty.
It's not pretty, but like it's working. And then I would say it's up to the BPF scheduler to decide if they want to use preferred mask or just ignore that.
Yeah.
Because it's
okay. I can add the SCADXT push as well. And the next one is we very likely will need ARC specific hooks to take out which CPUs. Tobias was doing some experiments around this and he saw stupendous gains when he takes out something on vertical lows on S390 instead of taking one core out. So maybe you can have a default one which just takes out the one core and maybe architecture specific one. If it is there, it can take out specific set of CPUs. Would that work?
So I would suggest having the default be a CPU that has significant recent idle time rather than whatever the highest CPU in the mask is.
Okay, well, that would be costly, right?
You're running this once a second.
Okay, we can think on that.
Yeah, so if your system then actually has affinities or CPU sets and is sparsely used, it'll pick the unused CPUs to drop off before, or the lesser used CPUs. But yeah, I don't know.
Yeah, and the still monitor can be, right now it's disabled by default, but our specific implementation where you just enable it unconditionally, something that.
And yeah, so we also have the active mask, and I'm wondering if we can use that.
That's sort of what CPU was doing with the partial hot plug.
We have any ABI there already? We have any ABI kind of a thing there?
So currently the active mask is only used during hot plug to bridge the gap between starting to take a CPU offline and it actually being offline with all CPUs pushed, with all tasks pushed off. And it's very close, but I'm not quite sure if it.
Then you still have cache rates and the CPU stuff.
Yeah, so the thing here is all the gate threads and all the other stuff, those should not be active if there isn't actually any users on that thing. So as long as you don't, this is also a no hertz assumption that if the CPU doesn't actually do anything, the kernel threads will also be, or at least the per CPU kernel threads will also be idle.
That's what we see. When run empty stat, zero utilization in all the rows, in all the columns of non-preferred CPUs.
Yeah, it's something I'll have to look at, but yeah. And it saves having yet another CPU manager. But.
So we put that part in the hot plug feature and use that. The partial hot plug thing was working for us when we abused this first mask. There were those kernel threads, and maybe
they eventually go quiet though.
Yeah, they will go. Yeah.
So we had those patches and they were tested.
I don't remember.
Well, it was some time.
It was some time ago. The kernel wasn't as good at quiet things down. We didn't do back then either. It was a bit more aggressive.
I have a quick question on to go back to the way you collect still time across CPUs. You don't need to scroll back, but it's more, what requirement do you have on the hypervisor in its way to expose still time? Do you need that to be globally visible, so one CPU can observe still time for all the other CPUs, or can it be strongly per CPU and it's each CPU that has to collect its own still time and expose it to whoever wants it?
Okay. Right now it's done by one CPU, so going across all the CPUs. So currently the still time is reported per CPU.
Yeah, and it can be private to the CPU. I mean, for example, on ARM64, we could absolutely report it in the per CPU register, in which case nobody else can see it.
But isn't the Linux still time API already exposing that more widely?
Procstat should give you the information.
It's a possibility. I don't know. I only care about the other side.
There's a still time clock thingy, like, and it has a CPU argument, and it'll give you the most recent observation from that CPU.
But it could be that so we have somewhere something that takes the per CPU view and exposes it.
Yeah, so all the KVM still time is in the vCPU shared page.
Yeah,
and it's yeah.
I think the current design, which only will let the CPU which have the still time above the threshold to not preferred mask. That is a possibility in the real world. It is just above the threshold, but still it have spare time, right? In the real system, not only benchmark test case, but the real use case. For example, one VM does some workload only above the threshold, but the physical CPU still have that spare capacity to be run with.
In that case, you should not even see still time. If physical capacity is there, you should not see still time.
I mean the threshold. It is not the total time, right?
It is the total sum time across all CPUs in the guest. The still time is today.
You mean for the scheduled tick time period? That means the threshold means all.
Yeah, still time is updated. Yes, at tick level.
Yeah, at tick level, it may 50% of the tick, right? Or 60% like a threshold, but still that CPU, you just rule it out.
Yeah. So to benefit the other CPUs, yes.
I think on 390, that really does make sense. Yes, we leave 40% on the table, but because we prevent, for example, local preemption, this is massive. So this is a trade-off.
Trade-off.
Yes.
So for different scenario, actually, it may have different results.
Yeah.
It takes advantage on the benchmarks.
Yeah. If you have workload inside the host, then all bets are off. This works only if hypervisor is doing minimal stuff. You're not doing any workload inside the host.
Another point is that we should take a holistic view. If we took a CPU from one VM, yes, this VM suffers, but we gave it to another VM that also needed it. And if we take the total throughput of these two VMs, that's still an improvement. That actually is going to be strict improvement. So it can be suboptimal if you view it at one VM, the single VM level. But if you look at it from the whole system level, even like sacrificing 40% in one VM is a net win. Because the other VM gets this time.
That's all we had. Thank you.